Hey everyone, in this video I'm going to be going over questions 1 through 6 of the USNCO 2025 local exam. You can follow along with both the solutions document I've made and the exam in the description below. So looking at the first problem, we can see that the essential conversion pathway we must go through is grams of N2O5 to moles of N2O5, then moles of nitrogen, and finally atoms of nitrogen. And some key numbers that are going to help us out here is that the molar mass of nitrogen is 14.01 grams per mole, and the molar mass of oxygen is 16 grams per mole. So going over to the problem here, we can see that the conversion seen right here, we're converting from grams to moles of N2O5 to moles of nitrogen, and then using Avogadro's number, we convert to atoms of nitrogen. So our answer is going to be C. Now for question 2, honestly, I'm just going to go over the answer choices one by one. So we know that the molar mass of sulfur is 32 grams per mole, and the molar mass of oxygen is 16 grams per mole. So we're looking for a 1-to-1 mass ratio because it's 50% sulfur and 50% oxygen. So, of course, you can do this in your head. It's SO2, but I'm just going to go through the answer choices. This would be 32 grams from sulfur and 16 grams from oxygen. This would be 32 grams from sulfur and 32 grams from oxygen. This would be 64 grams from sulfur and 16 grams from oxygen, and this would be 96 grams from sulfur and 64 grams for oxygen. So we want a 1-to-1 mass ratio, so that's going to end up being C. Now for this problem, essentially, let's just go through the conversion pathway again. We have grams of aluminum to moles of aluminum, then to moles of chlorine, and moles of Cl, and then 2 grams of chlorine. And essentially, what we want to find out is a reaction being described. So we have aluminum reacting with chlorine to make aluminum chloride, and that reaction is going to be this. It also works with the reaction Al plus 3Cl goes to AlCl3, but this is the more technically accurate way of writing it with the Cl2. And from there, we just do the dimensional analysis I described earlier, converting to grams of Al to moles of Al, then moles of Cl2, moles of Cl, and grams of chlorine. So our answer is going to end up being D. Now, as for number 4, essentially what we have here is a solution problem, right? So what I typically do is try to break down the problem. So we have 0.5 liters of 0.15 molar Ki, and we're adding that to 0.25 liters of 0.2 molar CaI2. Now, it's asking for the concentration of iodide, so that's going to be our moles of iodide over the liters of solution. And just to figure out how to find this moles of iodide, we take the liters of solution of each of these individual things, the individual solutions that we're mixing together, and we're going to multiply by the given molarity over 1 liter, and then the moles of iodide per mole of the substance that we have. And just to make that a bit more clear, we can see the actual solution here. We're just doing the same steps I described earlier. We have the liters of Ki, multiplying that by the molarity value. And then, since there's only 1 mole of iodide per mole of potassium iodide when it's dissolved, we get this number of moles of iodide. And doing the same thing here, we're going to get this value. So we're actually just going to add these together to find the total moles of iodide. And going back to the definition of concentration here, we need to find the liters of solution. We have 0.5 liters up here and 0.25 liters up here, making 0.75 liters of solution. and dividing those two, we get 0.233 molarity just by dividing these. So that's going to be our answer. Now, as for problem number 5, this is a word problem kind of. So you're going to want to break it down a bit. Essentially, we have this ore, and inside of that ore, there's malachite. And inside of that malachite and that malachite only, there's copper. Make sure you realize that the only source of copper in an ore sample is a mineral malachite. So yeah, essentially to figure out this problem, we know that we have the grams of copper here, right? And what we want to do is figure out the percentage by mass of which the ore is malachite. So we're going to convert this copper back into malachite and then divide that by the 1 kg of ore that we have. And more specifically, we're going to go from grams of copper to grams of malachite and then divide that by 1 kg of ore. So this is pretty much the same dimensional analysis that like the rest of the problems have been following, so I'm not going to go into it much in depth. So yeah, we're just converting from grams to copper, and then our end result is this gram value of malachite, and again we have this 1 kg of ore, 1,000 grams, and then multiplying our value here by 100% to get the percentage value, we get the answer B. Now for question 6, this is a colligative properties problem. So colligative properties are properties of a solution that depend on the amount of solute dissolved, not the actual properties of the solute. So the equation that we're looking for here, it asks for the highest boiling point. So that's a sign that we need to use the equation. The change in boiling point is equal to the Van 't Hoff factor times molality times Kb. And just to break this down more, I is our Van 't Hoff factor. So that's the number of ions that the substance dissolves into. And our molality here, or M, is going to be the number of moles of solute over the kgs of solvent, not the liters of solvent. That's molarity. And then here we have Kb, so this is a constant based on the solvent. So just going back to the problem here, we have water as a solvent for all of them, so Kb is not really going to be an issue. Instead, we're going to be looking at the Van 't Hoff factor and the molality the most. So in these types of problems, the Van 't Hoff factor will end up being like a bigger contributor to the change in boiling point than the molality. So we're going to want to look at that first and then sort of use the molality as a tiebreaker. So we're going to break down the Van 't Hoff factor of each of these. One key thing for choice number A, H2SO4, you know that as a strong acid. However, that does not automatically mean that it dissociates fully into everything it can dissociate into. Instead, being a strong acid means that it's going to dissociate into this H plus and this HSO4 fully. However, this dissociation further into H plus and then SO4 2 minus, that's not actually going to happen fully. So this dissociation is 100%. This is less than 100%. So our Van 't Hoff factor is going to end up being between 2 and 3, because we have these two for sure, and then a little bit from here. Yeah, so that's our Van 't Hoff factor for that. The rest of these Van 't Hoff factors for B, C, and D, that's just coming from our solubility rules. We know that all of these dissolve fully, so they're going to be the number of ions. So we have 1 magnesium ion, 1 sulfate ion, that's 2. Here it's 2 sodium ions, and then 1 sulfate, so it's 3. Same thing applies here, so it's 3. So going back to our equation, we know that we have the Van 't Hoff factor times molality. The Kb doesn't matter. So right now we kind of have a tie between sodium sulfate and lithium sulfate because they both have a Van't Hoff factor 3. So we're just going to look at the molality here. So essentially, the molar mass of Li2SO4 is less than the molar mass of sodium sulfate. So the molality is actually going to be higher. And that is because we have 10 grams of the substance for all the substances. So with a lower molar mass, you're able to get more moles out of the same amount of gram values, or out of the same weight of the substance. And of course, we're always dissolving in the same amount of water, so the denominator is the same. So yeah, lithium sulfate is going to be our answer because it has a higher IM value here. So our answer is lithium sulfate. And in the solution document, I've laid out a more complete, holistic solution of this. I'm not just like looking at the Van't Hoff factor first and then the molality. However, of course, on the exam, you most likely don't have time to do this. So you want to look at the Van't Hoff factor first and then the molality for most problems.